In 1545, a physician in Milan met a problem with a perfectly ordinary answer and found he could reach it only by walking through country he was certain did not exist. He wrote that the business was mental torture. He did the calculation anyway, shut the book, and called the result as subtle as it was useless. But 476 years later, in a laboratory outside the Chinese city of Hefei, a circuit chilled near absolute zero settled the question he walked away from. The answer surprised everyone. Let me take you back to the world that produced that moment, because the setting matters more than you might think. Picture Bologna in the early 1500s. Narrow arcaded streets, red brick towers leaning at unlikely angles. The oldest university in Europe, already 300 years old, and full of men in dark gowns arguing in Latin. Mathematics in that city ran a good deal closer to a blood sport than to a quiet profession. A mathematician did not hold a permanent chair the way a professor does today. He held a position that could be challenged, publicly, by any rival who fancied his salary. The challenger would deposit money with a notary. Each man would hand the other a sealed list of problems. They would agree on a date, usually 40 or 50 days later, and on that date, the answers would be read out in a hall or a church, or the courtyard of a palace, in front of an audience that had come for exactly the reason you would come to a boxing match. The winner took the money, and often the loser's job. Think about what that system does to knowledge. If your livelihood depends on being able to solve problems your rivals cannot, then a new method is not something you publish. It is something you hide. A technique nobody else possesses is a weapon, and you keep a weapon in a locked drawer. Secrecy in that world counted as ordinary professional caution rather than a moral failing, the same instinct that makes a modern company keep its source code private. The consequence, though, was that European mathematics advanced in fits and jerks, with long silences in between, and a great deal of it died quietly in the notebooks of men who never told anyone. Which brings us to the problem at the center of everything that follows. You already know how to solve a quadratic equation, or you did once, and the memory is probably somewhere near the memory of a green chalkboard and a summer afternoon. Something squared plus something times x plus a number equals 0. There is a formula. You learned it, you used it on a test, you forgot it, and it has been sitting patiently in the back of your mind ever since. That formula was old. Babylonian scribes were solving quadratic problems on clay tablets in the 2nd millennium before Christ, pressing wedge-shaped marks into wet clay in the cities of Mesopotamia. Islamic mathematicians in Baghdad refined the methods and gave the subject its name, algebra, the restoring, the moving of a term from one side of an equation to the other, algebra. But raise the power by 1 and everything falls apart. The cubic. X cubed plus x squared plus x plus a number equals 0. It looks like a small step up. It is not. For roughly 3,000 years, from those Babylonian tablets to the streets of Renaissance Italy, nobody could solve the general cubic equation. Omar Khayyam, who you may know better as a poet, attacked it in 11th century Persia with a beautiful geometric method involving intersecting conic sections, and got real answers out of it, but he could not produce a formula. Luca Pacioli, the Franciscan friar, who taught Leonardo da Vinci mathematics and who wrote the first printed book on double-entry bookkeeping, declared in 1494 that solving the cubic was as impossible as squaring the circle. That was the settled professional opinion. The best mathematician in Italy had looked at the problem and pronounced it beyond human reach. Part of the difficulty was one that will sound strange to modern ears. 16th century mathematicians did not accept negative numbers. A number, in that tradition, was a quantity of something, a length, a weight, a sum of money. You cannot have a stick that is -3 feet long. So a negative answer to an equation was not a solution, It was evidence that you had set the problem up wrongly, and because you could not write a negative coefficient, you could not write the general cubic as one equation. You had to write it as 13 separate cases, each with its own arrangement of terms, each requiring its own treatment. Cube and things equal to a number, then cube equal to things and a number, then cube and square equal to a number. 13 distinct problems wearing 13 distinct disguises, and no way to see that they were all the same animal. There was one simplification available, and it turned out to be the key to the door. If you take a general cubic and shift the variable slightly, replacing x with x minus a carefully chosen constant, the squared term vanishes. What you are left with is called the depressed cubic. Cube equals a multiple of the unknown, plus a number. Cleaner, simpler, and still, as far as anyone in Europe knew in the year 1500, completely unsolvable. Then, a lecturer at the University of Bologna solved it. His name was Scipione del Ferro. He was born in Bologna in 1465, the son of a papermaker, in the decades just after the printing press arrived in Italy and made paper a serious business. He held a chair in arithmetic and geometry at the university for 30 years, from 1496 until his death in 1526. And at some point around 1515, in circumstances nobody has ever recovered, he worked out how to solve the depressed cubic. We do not know how he did it. We do not know how long it took him, or what he felt when the last piece fell into place, or whether he sat for a while afterwards in the quiet of his study, looking at what he had written. What we know is what he did next, which was nothing. He published no paper, announced no result, and told almost no one. The method went into a small notebook in his own hand, and there it stayed. Understand that this was, at that moment, the most valuable secret in European mathematics. A man who could solve cubics could destroy any rival in a public contest, simply by setting him 30 cubic problems and waiting. Del Ferro never appears to have used it that way, at least not that history records, which is one of the small mysteries of the whole affair. He simply held it for 11 years, and then he died. On his deathbed, or shortly before it, he passed the notebook to two people. One was his son-in-law, a man named Hannibal della Nave, who inherited both the notebook and Del Ferro's chair at the university. The other was a student of his, a Venetian named Antonio Maria Fiore, who inherited only the method and nothing like the talent to extend it. Remember that notebook. It comes back 30 years later in a way that changes everything, and it is the hinge on which the second half of this story turns. Fiore, meanwhile, did exactly what Del Ferro had not done. He waited a few years, and then he went hunting. He had in his possession a weapon that no other mathematician in Europe could match, and he intended to use it to make his name. In 1535, he issued a public challenge to a schoolteacher in Venice, a man who had been going around claiming, implausibly, that he had solved the cubic himself. Fiore assumed the man was bluffing. Almost everyone did. It was the sort of claim that got made in that world, and it was almost never true. This time it was true, and the man making it had already survived something that should have killed him. His name, or rather the name he was known by, was Tartaglia. He did not choose it. The name was closer to a scar that had hardened into a word. He was born in Brescia, in Lombardy, in either 1499 or 1500. The uncertainty is itself part of the picture, because nobody bothered to record the birth precisely. His family had no surname anyone could rely on. His father was a mail rider named Michele, who carried letters on horseback between Brescia and the neighbouring towns, and who was murdered on the road when the boy was 6. Whatever thin security the household had, it went with him. The widow and her children fell into a poverty that the son remembered with great precision to the end of his days, and wrote about later without any softening. He had, by his own account, About 15 days of formal schooling. A tutor was hired to teach him the alphabet. The money ran out somewhere in the middle of the letter K. He stole a copybook, taught himself the rest, and kept going. Everything that man ever knew about mathematics, he taught himself, in a language he had also largely taught himself to read. Then, in the winter of 1512, the war came to Brescia. Northern Italy in those years was the board on which the great powers played. France, Spain, the Papal States, Venice, the Holy Roman Empire, all of them moving armies across the Lombard Plain and through the walled towns of the Po Valley. Brescia had been under French control, had risen in revolt in favour of Venice, and in February of 1512, a French army under Gaston de Foix, the Duke of Nemours, came to take it back. He was 22 years old, the nephew of the King of France, and by every account, a brilliant and utterly ruthless soldier. His men entered the city and were given it. The sack of Brescia lasted several days. Contemporary accounts put the number of dead in the thousands, and while medieval and Renaissance casualty figures should always be held loosely, no source describes it as anything other than a catastrophe. Houses were emptied, churches were emptied, the city that had been one of the wealthier towns in Lombardy was stripped to the walls. The boy was 12. His mother took her children into the cathedral, which is what you did, because sanctuary was supposed to mean something. It did not. Soldiers came into the cathedral, and one of them struck the boy across the face with a sabre. The blade went through his jaw and split his palate. He was left for dead among the dead. His mother found him alive. There was no surgeon, no money for one, and no expectation that a wound like that could be treated. She is said to have done the only thing she could think of, which was to keep the wound clean and let it close on its own, the way she had watched dogs heal themselves. It worked well enough that he lived. It did not work well enough that he could speak properly again. The damage to his palate left him with a permanent, laboured stammer. He grew a beard as soon as he could, and wore it for the rest of his life to cover the scarring. And the children of Brescia, being children, gave him a name for the way he talked. Tartaglia, the Stammerer. He took it, and that is the detail that stays with me. He could have used any name he liked once he left the city and made himself into a mathematician. The books he wrote later are all signed Niccolo Tartaglia. He carried the insult forward on purpose, printed it on title pages, and made it the name that 400 years of mathematicians would use with respect. By 1534, he had moved to Venice and was teaching mathematics for a living, which meant teaching arithmetic to merchants and gunners and anyone else who needed to calculate for practical reasons. He was good at the practical end of things. He wrote the first serious study of the trajectory of cannonballs, and he was the first person to state in print that a gun fired at 45 degrees achieves maximum range, which was the sort of finding that got a man noticed by people with money. And in the early 1530s, working alone, with no university and no teacher and no access to Del Ferro's notebook, he solved the depressed cubic himself. He announced it. Of course he did. He had spent his whole life being underestimated, and here, at last, was something nobody could take from him. He may not have realized, when Fiore's challenge arrived, that the man on the other side of it held the same secret from a different source. The rules were set. 30 problems each, deposited with a notary in Venice, 50 days to answer, and a dinner for the winner's party, paid for by the loser, for every problem solved. Fiore, working from Del Ferro's method, submitted 30 problems that were all of the same type, cube and things equal to a number. He had one weapon, and he swung it 30 times. Tartaglia submitted 30 problems of many different kinds, because he was the better mathematician, and he knew it. Then he sat down to worry, because he had solved one form of the depressed cubic, and he could see, from the shape of Fiore's list, that Fiore had a general method for a form he had not yet cracked. He had 8 days left. On the 13th of February, 1535, with the deadline closing, Niccolo Tartaglia found the rest of it. He solved the remaining case, and then he solved all 30 of Fiore's problems in under 2 hours. Fiore solved none of Tartaglia's. The stammerer from Brescia, with 15 days of schooling and a face he kept covered, had beaten the inheritor of the greatest secret in Italian mathematics, and he did it in public, and everyone saw. He declined the dinners. He said the honor was enough. News of that contest travelled, and it travelled fast, and it reached Milan, where a man was reading about it with an interest that was not entirely academic. He was a physician, an astrologer, a compulsive gambler, and among the most restlessly curious minds of the century. His name was Girolamo Cardano, and he wanted that formula more than he had ever wanted anything. Girolamo Cardano is difficult to describe briefly, because almost nothing about him was ordinary. He was born in Pavia in 1501, the illegitimate son of a lawyer who was also a mathematician, and who had known Leonardo da Vinci well enough to be consulted by him on questions of geometry. That illegitimacy shaped his early career the way a stone shapes a river. The College of Physicians in Milan refused him admission for years on those grounds, and he spent a long stretch practicing medicine in a small town in the countryside, treating farmers, going broke, and gambling to make up the difference. He was, by his own cheerful admission, addicted to gambling, chess, dice, cards, anything with a stake on it. He once wrote that he had gambled every day for 40 years. What makes that detail worth telling is what he did with it. He sat down and wrote a book called The Book on Games of Chance, in which he worked out, essentially for the first time in European history, how to calculate the odds of dice throws. It contains the first serious mathematical treatment of probability anywhere. He wrote it around 1564, and then, in a decision that tells you a great deal about the man, he did not publish it because he did not want to give away an advantage at the table. It came out in 1663, nearly 90 years after his death. By the mid-1530s, his reputation had begun to turn. He talked his way into public lectures, cured patients other doctors had given up on, wrote a scathing book about the incompetence of the medical profession, and eventually became the most sought-after physician in Europe. He would later be summoned all the way to Scotland to treat the Archbishop of St. Andrews for asthma, and would cure him, apparently by suggesting he stop sleeping on a feather pillow. That was the man who wrote to Tartaglia in 1539. He was polite at first, and then less polite, and finally he did the thing that worked. He wrote that he had been asked to arrange an introduction for Tartaglia to the Marchese del Vasto, the Spanish governor of Milan, a man in a position to award pensions and patronage to a mathematician with useful ideas about artillery. Tartaglia, who was poor and had always been poor, and who had a great deal to say about the trajectory of cannonballs, came to Milan in March of 1539. The governor was away. Cardano and Tartaglia spent several days together in Cardano's house instead, talking. And on the 25th of March in that house, Tartaglia gave him the method. He did not write it as an equation, because nobody wrote equations in the modern sense yet. He wrote it as a poem, 25 lines of Italian verse, rhymed, so that the method could be memorized the way you memorize a song. It begins with the instruction to find two numbers whose difference is the known quantity and whose product is the cube of a third of the other coefficient. Renaissance mathematics in a nutshell. A general algorithm, encoded as poetry, handed over in a private room. And before he handed it over, he made Cardano swear an oath. Not a handshake, a sworn oath, on the Holy Gospels, as a true Christian, never to publish the method, and to write it down only in cipher, so that after his death, nobody would be able to understand it. Cardano swore it, Tartaglia went home, and the governor never gave him anything. For 6 years, Cardano kept the oath. He also did something with the method that Tartaglia had not done, which was to give it to a 19-year-old servant boy in his household named Lodovico Ferrari. Ferrari had come to Cardano's door at 14, looking for work as a domestic. Cardano discovered that the boy could read, then discovered that the boy could do considerably more than read, and made him a secretary and then a student. And Ferrari, working from the cubic method, did something extraordinary. He solved the quartic, the fourth-degree equation, x to the fourth, which nobody had ever cracked, fell to a technique he built on top of Tartaglia's formula, which put Cardano in a genuinely miserable position. His student had made a discovery of the first rank. It could not be published, because publishing it meant publishing the cubic method it depended on, and the cubic method was under oath. Ferrari's work was locked in a box to which Tartaglia held the key, and Tartaglia had no intention of turning it. So in 1543, Cardano and Ferrari got on horses and rode to Bologna. They went to see Hannibal della Nave, who had been Scipione del Ferro's student, had married his daughter, and had taken over his chair at the university. Della Nave was, by Ferrari's later description, a clever and humane man, and he showed them something. He brought out a little book, in Del Ferro's own hand, written long before, in which the solution of the depressed cubic was set out elegantly and learnedly. Cardano stood in that room in Bologna and read the formula he had sworn never to publish, in the handwriting of a man who had died in 1526, written down years before Tartaglia had ever set eyes on it. You can feel the argument he made to himself, because it is not an unreasonable one. The oath was sworn over Tartaglia's discovery, but the discovery was not Tartaglia's, or not only his. Del Ferro had it first by 20 years. Tartaglia had rediscovered something that already existed, and the priority belonged to a dead man in Bologna whose son-in-law had just shown it to them freely. An oath protecting a secret that was not a secret protects nothing. 2 years later, in 1545, Cardano published the Ars Magna, the Great Art, and it changed the shape of algebra permanently. It is a genuinely magnificent book. Inside it you find the solution of the cubic in all 13 cases, and Ferrari's solution of the quartic. This is also the first place anyone treats negative solutions as solutions rather than errors, though Cardano calls them fictitious and is plainly uncomfortable. The book stands alongside Copernicus on the heavens and Vesalius on the human body as one of the founding scientific texts of the century, all three first published within 2 years of each other, in a burst of print that reads now like the moment Europe changed its mind about what could be known. And Cardano credited his sources. Chapter 11 opens by stating that Scipione del Ferro of Bologna discovered the rule nearly 30 years ago and passed it to Antonio Maria Fiore of Venice, whose contest with Niccolo Tartaglia of Brescia gave Niccolo the occasion to find it. He names del Ferro first, Tartaglia second, and gives Ferrari full credit for the quartic. By the publishing standards of 1545, when attribution was casual at best, this is scrupulous. Tartaglia did not see it that way, and it is worth pausing on why, because the usual telling makes him sound merely petty, and he deserves better than that. He was a man who had been given nothing, no education, no father, no money, no protection, no face he was willing to show. Everything he had taken by force of will out of a world that had tried fairly hard to kill him. The cubic formula was the one thing in his life that was unambiguously his own, earned in the dark by his own effort, and validated in public against the man who had inherited it. Cardano was a wealthy physician with a house in Milan, a Latin education, and a printer. He had asked for the secret, been given it as a gift, sworn on the Gospels, and then printed it under his own name in a book that would carry his reputation for centuries. Tartaglia responded with a book of his own the following year, New Problems and Inventions, which reprints what he says are the letters and the word-for-word conversations, and which reads exactly like what it is, a man setting the record straight at the top of his voice. Cardano, at the height of his fame, ignored him completely and let Ferrari answer. Ferrari, who was young and hot-tempered and utterly devoted to his master, issued a challenge, and in 1548 the two of them met in a church in Milan for a public debate. The accounts of what happened are partisan on both sides. What is agreed is that the audience was largely Ferrari's, that the argument went badly for Tartaglia, and that he left Milan overnight before the second day. He went back to Brescia, to a teaching post he had been promised, taught for a year, and was not paid. The lawsuit he brought over it went against him. Venice took him back, and he died there in 1557, poor, in the same district he had lived in for most of his adult life. There is one more thing to say for him, because the feud has swallowed his reputation, and he was a considerably larger figure than the man who lost an argument with a physician. In 1543, 2 years before the Ars Magna appeared, Tartaglia published a translation of Euclid's Elements into Italian. It was the first time the Elements had been printed in any modern European language, and that mattered more than the sentence suggests. For centuries, Europe had been reading Euclid through Latin versions made from Arabic intermediaries, and parts of those texts had degraded along the chain of translation into something close to unusable. Tartaglia went at it properly, with commentary, in the language that literate Italians actually read, and it was still being reprinted decades after his death. In the same year, he produced the first printed edition of a 13th-century Latin translation of some of the works of Archimedes, and later an Italian version of them as well. A man with 15 days of schooling handed the Renaissance back 2 of its Greek foundations. He also worked out how to find the volume of a tetrahedron from the lengths of its 6 edges, a formula that still carries his name and that surveyors and crystallographers still use. And he wrote down the triangle of binomial coefficients that most of us met at school as Pascal's triangle, a century before Pascal was born. In Italy they call it Tartaglia's triangle, and they are not being sentimental about it. He never forgave Cardano, and the formula that both of them fought over is called the Cardano formula in every textbook printed since. Cardano's own later life was not a soft landing either, and it belongs in the record because the telling usually leaves him standing in triumph. In 1560, his elder son Giambattista, a physician like his father, was arrested for poisoning his wife. He had married badly and unhappily, and he confessed. Cardano spent everything he had on the defense, worked every connection he possessed, and could not save him. The young man was executed in Milan at 26. His father wrote afterwards that it was the worst thing that had ever befallen him, and everyone who knew him agreed that he never entirely recovered. 10 years later, in 1570, Cardano was arrested by the Inquisition. The charge was heresy, and the offence was that he had published a horoscope of Jesus Christ, which was taken to mean that the events of the life of Christ had been governed by the stars. He was held for some months, recanted, was barred from teaching and from further publication, and went to Rome, where he was eventually granted a pension and admitted to the College of Physicians that had once refused him. He spent his last years writing an autobiography of startling candour, in which he lists his own faults at length, gambling among them, and says of his life that he had been given a good mind and very little else, and had done what he could with it. 2 men then, both of them damaged early, both of them formidable, arguing across 4 centuries about a formula that neither of them had invented. That is the human story, and it is a good one. But it is not the reason any of this matters, and if you take only the feud away from tonight, you will have taken the small half. Because inside that formula, sitting quietly in the middle of it, was a trap that neither of them put there and neither of them could remove. It had been waiting since Del Ferro first wrote the method down in Bologna, and it is the single most important fact in this entire story. So I want to build it slowly and carefully and make sure it lands properly, because everything that follows for the next 4 centuries comes out of it. Here is the shape of the formula. You have a depressed cubic. X cubed equals some multiple of x plus a number. The recipe tells you to take the number, halve it, and square the result. Then take the coefficient of x, divide it by 3, and cube the result. You subtract the second from the first, and you take the square root of what remains. Then you add that square root to the halved number, and take the cube root of the whole thing, and you subtract that square root from the halved number, and take the cube root of that too, and you add the 2 cube roots together. That sum is your answer. 2 cube roots, and inside each of them, a square root. Now, everything in that recipe is a perfectly ordinary operation on perfectly ordinary numbers, as long as the thing under the square root is positive. And for a great many cubics, it is positive, and the machine hums along and gives you a clean answer, and there is no trouble at all. But consider what happens when a cubic has 3 real solutions. A cubic curve, drawn on paper, is that familiar sinuous S shape. Depending on how it sits, it might cross the horizontal axis once, or it might wander up, come back down, and go up again, crossing 3 times. 3 crossings, 3 real roots, and 3 ordinary findable answers with nothing exotic about them. You could measure them with a ruler if the drawing were accurate enough. Those are the friendliest cubics there are, the ones with the most answers, all of them real, all of them visible. And those are precisely the ones where the formula breaks. When a cubic has 3 distinct real roots, the quantity under that square root is always negative, always. Not sometimes, not in awkward edge cases. It is a theorem, and it has a name, and the name is one of the loveliest pieces of terminology in mathematics. The casus irreducibilis, the irreducible case. Sit with the shape of that for a moment, because it is genuinely strange. You begin with an equation whose coefficients are ordinary whole numbers. You are looking for answers which are ordinary real numbers, 3 of them, sitting there on the number line where anyone can point at them. And the only general algebraic route from the question to the answers runs directly through the square root of a negative quantity. Real question in, real answer out. Impossible territory in between, unavoidably, every single time. And it truly is unavoidable. That is not a limitation of Cardano's particular recipe or of 16th century cleverness. It was proved rigorously in 1843 by a young French mathematician named Pierre Wancel, the same man who had already settled the 2 great impossibilities of Greek geometry by showing that you cannot trisect an arbitrary angle or double a cube with compass and straight edge alone. Wancel worked in the evenings, read late, slept badly, and in short, broken stretches, and by the account of the friend who wrote his obituary, made alternately bad use of coffee and of opium, trusting a constitution that was strong until it was not. He died in Paris at 33. His theorem was so thoroughly forgotten that 2 other mathematicians proved it again decades later and are still sometimes given the credit. But it was his, and it stands today exactly as he left it. In the case of 3 distinct real roots, there is no way to express those roots using real radicals alone. You cannot find a better formula, because a better formula does not exist, which means the detour is the road, and there has never been another one. Now put yourself in the room with Cardano in 1545, looking at that. He did not have 400 years of hindsight. He had a number line on which negative numbers were already suspicious guests, and on that line every number, positive or negative, gives a positive result when multiplied by itself. Positive times positive is positive. Negative times negative is also positive. So nothing on the line squares to give a negative. Finding the square root of -15 is not a matter of difficulty. No such number can be there at all. Asking for it is not posing a hard question with an elusive answer. You are requesting something the universe of numbers, as he understood it, simply does not contain. And his formula was demanding that he pass through it in order to reach answers he could already see. He wrote about them exactly as you would expect a careful man to write about something that offends him. He called such quantities sophistic, which in the Latin of the period means the kind of thing a clever arguer produces to win a debate rather than to tell the truth. And he said that calculating with them was mental torture. That phrase deserves a closer look, because there is a joke buried in it that most tellings miss. In chapter 37 of the Ars Magna, near the end of the book, Cardano sets a small puzzle. Divide 10 into two parts whose product is 40. In modern terms, find two numbers that add to 10 and multiply to 40. Try it in your head for a moment as you lie there. 5 and 5 gives you a product of 25. Push them apart, 6 and 4, and you get 24. Every way you split 10, the product goes down from 25, never up. 40 is out of reach. The problem, as he says himself, is manifestly impossible. He does it anyway. He completes the square, follows the algebra where it goes, and out comes the answer. 5 plus the square root of -15, and 5 minus the square root of -15. Having produced two quantities he has just declared cannot exist, he multiplies them together. He writes the Latin phrase dismissis in cruciationibus, and he carries out the multiplication. 5 plus that root times 5 minus that root. The cross terms cancel. You are left with 25 minus the quantity minus 15, which is 25 plus 15, which is 40. Exactly 40. The impossible answer to the impossible question, checked and confirmed. That is the first calculation with complex numbers ever performed in the history of mathematics, and it sits in chapter 37 of a book about cubic equations, treated as a curiosity. Now, that Latin phrase, dismissis in cruciationibus, it is usually translated putting aside the mental tortures, and the word in cruciationibus does carry that meaning, but the root of it is crux, a cross. Translators have long noticed that Cardano is very probably making a pun, because the phrase can equally be read as the cross multiples having cancelled out, which is precisely the arithmetic step he is performing at that moment. The cross terms cancel. The torment is dismissed, both at once, in 2 words, in a book on algebra. A tired, brilliant, gambling physician, making a joke in Latin about how much he dislikes what his own mathematics has just handed him. Then he closes the door. His verdict on the whole business is that arithmetical subtlety extends this far, and that this, its furthest point, is as subtle as it is useless. He was wrong about that. He was wrong in a way that took 400 years and several thousand people to become fully clear. But look at how close he came. He wrote the numbers down, he gave them arithmetic, checked that arithmetic, and found it entirely consistent. Then he stood at the doorway of the entire complex plane with a lamp in his hand, looked in, decided there was nothing worth having in there, and went to bed. Somebody was going to have to go back in, and the man who did was not a professor or a physician or anyone the universities of Italy would have recognized as a mathematician at all. He was an engineer who spent his working life standing in a marsh. Raphael Bombelli was baptized in Bologna on the 20th of January, 1526. which is the same year Scipione del Ferro died in that city. The two of them may have passed each other in the street. Bombelli's family had lost everything a generation earlier for political reasons, his grandfather having been on the wrong side of a failed rising against the ruling family, and by the time Raphael was born, they were wool traders rather than gentry. He did not go to university. There is no record of him attending any school of mathematics, and the men who taught in Bologna's lecture halls appear never to have heard of him. What he had instead was an apprenticeship to an engineer and architect named Pier Francesco Clementi, and a talent that grew in the open air rather than in a library. His profession was hydraulic engineering, which in 16th century Italy was serious, well-paid, politically sensitive work. Rivers silted up, marshes bred malaria and swallowed farmland, and towns flooded. And the men who could survey a wetland, calculate a gradient, plan a drainage channel, and get the water to leave were in permanent demand from anyone who owned land and wanted it dry. His patron was Alessandro Ruffini, a Roman nobleman who later became the Bishop of Melfi, and the project was the reclamation of the Val di Chiana. If you have driven through Tuscany between Arezzo and Chiusi, you have passed through it. Broad, flat, green, densely farmed, entirely unremarkable to look at. In Bombelli's day, it was a stagnant marsh, and had been for centuries, because the valley sits on a watershed so nearly level that the water in it could not decide which way to go. Some of it drained north to the Arno, and some south to the Tiber, and in between it simply sat, spreading sideways, breeding mosquitoes and fever. Draining it was one of the great engineering projects of the Italian Renaissance, and it went on in fits and starts for 300 years. Bombelli worked on it in the 1550s. He was, by all accounts, extremely good at it. He later reclaimed marshland in the Roman Campagna, and he was called in on the perpetual, exhausting problem of the Tiber flooding Rome. Then, sometime in the 1550s, the reclamation work was suspended. Funding, politics, the usual reasons. Bombelli found himself with an interval of unexpected free time and a patron's villa to sit in. So he wrote a book about algebra. Think about the position he was in. He had read the Ars Magna. By his own account, he had also read essentially everything else available and had formed a firm opinion, which was that the existing literature was a mess. He wrote that the material was either too difficult or too confusedly written, and that the more perfect algebra became, the less clearly he could see it explained by the people writing about it. His stated aim was to remove every obstacle for those who were curious about the subject, and to take away every excuse from the lazy and the incompetent, which is, if you think about it, the exact voice of a working engineer who has been handed a badly written manual once too often. His book was called L'Algebra. It came out in 1572 in Bologna, printed by Giovanni Rossi. He died that same year at 46 and never saw what it became. There is one more thing he did in between, and it is worth a moment because it is such a strange piece of good fortune. While in Rome, he met a papal librarian named Antonio Maria Pazzi, and the two of them went into the Vatican Library and found a manuscript of the Arithmetica of Diophantus of Alexandria, a Greek text from the 3rd century that had been almost entirely lost to Western Europe. The two men sat down and worked through it. Bombelli was so taken with it that he rewrote large parts of his own book to incorporate what he had learned, and he reproduced 143 of Diophantus's problems in his own pages. That same Arithmetica, in a later printed edition, is the book in whose margin Pierre de Fermat would one day write the note about having a marvellous proof for which the margin was too narrow. Bombelli helped pull it back into the light. But the reason we are talking about him tonight is a single passage, and a phrase he used to describe his own thinking. He called it a wild thought. He was looking at the casus irreducibilis, at the same trap Cardano had walked away from, and he chose an example that made the absurdity as sharp as possible. X cubed equals 15x plus 4. Solve that in your head, and it will not take long. Try 4. 4 cubed is 64, and 15 times 4 is 60, and 60 plus 4 is 64. It works, and the answer is 4, a whole number, small, obvious, sitting there in plain view. Now put the same equation through Cardano's formula. Halve the 4, giving 2. Square it, giving 4. Take the 15, divide by 3, giving 5. Cube it, giving 125. 4 minus 125 is minus 121. Take the square root of that. The square root of minus 121. And so the formula reports that the answer is the cube root of 2 plus the square root of minus 121, added to the cube root of 2 minus the square root of minus 121. Two monstrous expressions, each containing a quantity that does not exist, and their sum, allegedly, is 4, a number you could count on your fingers. Cardano saw that, and concluded the formula had reached the edge of its usefulness. Bombelli saw it, and concluded something else entirely, which is that the formula was not lying. It had never lied before. Every time you could check it, it was right. Why would it start lying now, on the easy cases? So he had his wild thought. It went like this. The two expressions are mirror images of each other, identical except that one has a plus where the other has a minus. Suppose their cube roots are mirror images too. Suppose the cube root of 2 plus that impossible quantity is itself of the form some ordinary number plus some quantity of the impossible kind, and suppose the other cube root is the same ordinary number minus the same impossible quantity. If that is so, then when you add them, the impossible parts cancel. They are equal and opposite. They vanish, and what is left is twice the ordinary number. And that is a perfectly real answer. That is the whole idea. It is almost embarrassingly simple, and it is a genuinely great moment in the history of thought. And the man who had it was a drainage engineer working in a borrowed villa. Then he did the hard part, which was to make it work numerically. He supposed the ordinary part was some number A, and the impossible part was B of the new kind, and he cubed the expression, keeping careful track of what happened when the impossible quantity multiplied itself. He knew what it had to do. Something whose square is -1 squared gives -1. He worked through it and found that A had to be 2 and B had to be 1. So the cube root of 2 plus the square root of -121 is 2 plus 1 of the impossible thing, and the other cube root is 2 minus 1 of it. Add them, and the impossible parts cancel exactly. 2 plus 2 is 4. 4. The answer he already knew, arrived at down the road that ran through nowhere. And this is the piece to hold on to, the piece that makes it different from a party trick. Bombelli did not prove that the square root of a negative number exists. He proved something more useful and, in a way, more disturbing. He proved that if you allow it into your arithmetic and treat it consistently, it behaves, it obeys rules, cancels when it should, and never gives you a wrong answer about the real world. Whatever the thing is, it behaves like a citizen rather than like chaos. He gave it a name because he was a practical man, and practical men name their tools. The plus version he called più di meno, which is Italian for more of less. The minus version was meno di meno, less of less, not the square root of -1, which is a description of a problem, but a name for a thing. Then he wrote out the multiplication table. More of less times more of less makes less. Less of less times less of less makes less. More of less times less of less makes more. In modern terms, I times I is -1, minus I times minus I is -1, I times minus I is +1. He set down the arithmetic of the complex numbers, correctly, in Bologna. in 1572, in a book whose author had never been to university. He also said, with a candour I find rather moving, that the whole matter seemed to rest on sophistry rather than truth. Bombelli was not sure what he had, and did it anyway, because it worked. That is the moment the square root of -1 stops being an error message and starts being a number. Then, for the better part of a century, essentially nothing happened. Not because nobody read Bombelli. He was read, and read carefully. Leibniz taught himself algebra from l'algebra, and called Bombelli an outstanding master of the analytical art. The book was influential precisely among the people who mattered. The trouble was that reading it did not tell you what these things were. You had rules for manipulating them. You had no picture, no meaning, no place to put them, and mathematics in the 17th century, still deeply tied to geometry, was very uncomfortable with a quantity that could not be drawn. Which brings us to the moment somebody gave them a name, and gave them the wrong one, and stuck the whole subject with it for 400 years. René Descartes was, by any reasonable measure, one of the 2 or 3 most consequential thinkers of his century. In 1637, he published a book called The Discourse on Method, and appended to it 3 essays showing what his method could do. The third of those essays was called La Géométrie, and it is the book in which coordinates enter mathematics, the x-axis and the y-axis, the idea that a curve and an equation are the same object seen 2 ways, the whole apparatus that lets you graph a function. That is his. And in La Géométrie, he made a passing remark about the roots of equations. He observed that an equation of degree n has n roots, but that not all of them correspond to real quantities. Some, he said, are merely imaginary. He meant it dismissively, and in his own terms he was being consistent. His entire project was the marriage of algebra to geometry. A root that was real was a root you could construct, draw, mark on a figure with compass and rule. The others could be written but not drawn. They existed only in imagination, imaginary. He was not proposing a technical term. He was making a remark, and it became the technical term anyway, and it is still the technical term on every blackboard in every school in the English-speaking world. I want to be careful here, because it is easy to make Descartes the villain, and he was not one. He also, in that same work, gave us the standard form we still use, the idea of writing such a quantity as an ordinary number plus a multiple of the strange one. That form is his. The naming was carelessness rather than malice. But think about what that word has done. A 10-year-old meets the term imaginary number before meeting the concept. The word arrives first and does all the work. It tells the child, in advance of any explanation, that this thing is not real, that it is invented, that it is a fiction adults use for reasons that will be explained later and never quite are. Every teacher who has ever tried to explain complex numbers has had to fight the name before getting anywhere near the mathematics, and most of them lose, because a word learned at 10 is stronger than an argument heard at 16. And the word is wrong. It is wrong in the plainest possible way. There is nothing more imaginary about I than there is about the square root of 2, which cannot be written as a fraction, and drove the Pythagoreans to something close to a spiritual crisis. Or about 0, which took Europe several centuries to accept as a number at all. Or about negative numbers, which Cardano himself still called fictitious in the very book we have been discussing. Every enlargement of the number system has been resisted with the same argument, that the new things are not really numbers, and every one of those arguments has lost. If I could reach back and change one thing about this story, it would not be the theft of the cubic formula, it would be that word. Meanwhile, quietly, somebody had the right idea, and nobody listened. John Wallis was the civilian professor of geometry at Oxford, a founding member of the Royal Society, and as fine a mathematician as England produced before Newton. He was also a codebreaker for Parliament during the Civil War, decrypting royalist dispatches, which is a nice detail for a man who spent his life turning obscure symbols into meaning. In a treatise on algebra, published in 1685, Wallace proposed something startling. If positive numbers run to the right along a line, he suggested, and negative numbers run to the left, then perhaps the impossible quantities do not belong on that line at all. Perhaps they should be measured off the line, at right angles to it, in a second dimension. That is, essentially, the answer. It was published in English by the civilian professor at Oxford in the middle of the 1680s by a man everyone in European mathematics knew. And it went nowhere. His treatment was tangled up with other things, his geometric constructions were awkward, and nobody picked it up. The idea would have to be found again, twice, more than a century later, by two men who had never heard of him. Then came Euler, who touched everything. Leonhard Euler was Swiss, spent most of his career in St. Petersburg and Berlin, went blind in the second half of his life, and continued producing mathematics at a rate that has never been matched by anyone, dictating to assistants. Around 1740, he found the relation that connects the exponential function to the sine and the cosine, which we will come back to at the end of tonight, because it is the resolution of this whole story, and it deserves its own quiet moment. And in a memoir of 1777, Euler introduced a symbol. For the quantity whose square is -1, he proposed writing simply the letter I. Small thing, enormous consequence. A name that fits on a page, that can be manipulated without dragging a radical sign around, that lets you write and think fluently. Notation is not decoration. Notation is the difference between an idea you can carry and an idea you have to keep unpacking. So by the end of the 18th century, the state of affairs was this. These quantities had arithmetic, thanks to a drainage engineer. They had a standard form and an unfortunate name, thanks to a philosopher, and a symbol, thanks to Euler. The best mathematicians alive were using them productively every week. And nobody had the faintest idea what they were. That question was about to be answered, definitively and beautifully, by two men working independently, neither of whom was a mathematician by profession, neither of whom got any credit at the time, and one of whom left his own name off the title page. Caspar Wessel was born in 1745 in a parsonage in Vestby, in Norway, the sixth of 13 children of a Lutheran minister. There were no universities in Norway at the time, so Norwegians who wanted an education went to Copenhagen, and two of his brothers had already gone. One of them, Johann Hermann Wessel, became a famous poet, the sort of national literary figure whose lines schoolchildren still learn. Johann Hermann once described his quiet brother in a single sentence. He draws maps and reads the law. He is as diligent as I am lazy. Caspar went to Copenhagen at 19, ran out of money almost immediately, and took work as an assistant surveyor to his older brother on the Royal Danish Academy's topographical survey of Denmark. He never left that work. He surveyed for over 40 years, through Denmark, Schleswig, Holstein, and the Duchy of Oldenburg, took a single sabbatical year to finish a law degree, and rose eventually to Royal Inspector of Surveying. His map of Schleswig and Holstein was good enough that Napoleon asked for a copy. No portrait of him is known to survive. We have his maps and one mathematical paper, and that sentence from his brother. Surveying is where the idea came from, and it makes complete sense once you see it. A surveyor does not think in quantities. He thinks in directed segments. From this trig point, 200 meters in that direction, then turn through this angle and go a further 140. Everything is a length together with a direction, and the whole trade consists of adding such things up and having them close properly. Wessel spent decades doing that, with chains and theodolites on cold Danish fields, and somewhere in there he began to wonder whether there was an algebra for it, not an algebra of quantities, but an algebra of directions. He wrote it up. One paper, in Danish, titled On the Analytical Representation of Direction. He was not a member of the Royal Danish Academy and had no standing to submit anything to it, but the Academy had relaxed its rule the previous year to allow papers from non-members, and the philosopher Johann Nicolaus Tettens presented it on his behalf on the 10th of March, 1797. It was the first paper by a non-member the Academy ever accepted. It was published in the Academy's memoirs in 1799, in Danish, in a journal almost nobody outside Denmark read, and it sat there, correct and complete and entirely unread, for 98 years. Jean-Robert Argand was born in Geneva in 1768 and spent his working life in Paris as a bookkeeper. Some sources suggest he ran a bookshop, others that he was a watchmaker at some point. Nobody is certain. He had no mathematical training that anyone has been able to document, no position, no teacher, no correspondence with the great figures of the day. In 1806, he wrote a short essay on how to represent imaginary quantities in geometric constructions, and had it printed at his own expense, in a very small number of copies, which he handed to people privately. He left his name off it. Call that modesty if you like. It reads more like a man who does not entirely believe he is allowed in the conversation. He had one copy delivered to Adrien Marie Legendre, one of the leading mathematicians in France. By one account, he met Legendre in person, pressed the manuscript on him, urged him to read it, and left. And only after he had gone did Legendre realize that the thing in his hands carried neither a name nor an address. Legendre's reaction was polite and unenthusiastic, and Argand, who seems to have been genuinely shy, let the matter drop. What happened next is one of my favorite sequences in the history of mathematics, and it turns entirely on chance. Legendre passed the anonymous pamphlet on to a friend, an army officer and mathematician named François Francais, in a letter dated the 2nd of November, 1806. Francais read it, kept it, and told nobody. He died in 1810. His brother, Jacques Francais, who was also a mathematician, went through his papers after the funeral and found the little book. He read it, understood what he was looking at, developed the ideas further, and in September of 1813 published them in Gergon's Annales de Mathématiques, a French mathematical journal. And in the last paragraph of that paper, he did the honourable thing. He wrote that the central ideas were not his. He had found them in a letter from Legendre among his dead brother's papers, describing the work of an author he could not name, and he asked that author, whoever he was, to come forward. 2 months later, in the November issue, Argand came forward. He identified himself, acknowledged the pamphlet, and published a fuller version of his argument. And that is how the man's name got attached to the idea. Not through publication, not through recognition, but because someone died, someone else went through the papers, and someone asked politely in print for a stranger to identify himself. Today, in schools everywhere, the picture is called the Argand diagram. Wessel had it first by 9 years and published it properly, and got nothing because he wrote in Danish. His paper was finally noticed in 1895, when a Danish mathematician named Christian Juhl drew attention to it, and Sophus Lee republished it that same year, and it was translated into French for the 100th anniversary, 98 years late. 2 men then, a surveyor in Copenhagen and a bookkeeper in Paris, neither of them professionals, both of them ignored, and both of them, independently, saw the same thing. Here it is. This is the center of tonight, and I want to walk through it slowly. Take an ordinary number line, running left to right, with 0 in the middle. Now ask what multiplication does to a point on that line. Multiply the number 1 by -1. You get -1. You started 1 unit to the right of 0, and you ended 1 unit to the left. Now, you could describe that as a reflection, and that is how most of us were taught to think about it. But there is another description, and it is equally accurate. You could say the point swung round through a half circle, 180 degrees, pivoting on 0, from the right-hand side to the left. Multiply by -1 again, and it swings back. Another half turn, and you are home at 1. 2 half turns make a full circle, and this is consistent with the arithmetic, because -1 times -1 is +1, which is exactly what a full turn should give you. Leave the number where it started. So multiplying by -1 is a rotation through half a turn. Now hold that and ask the question that had been tormenting mathematics for 250 years, but ask it in this new language. What is the number whose square is -1? Which is to say, what is the operation that, applied twice, gives you a half turn? And the answer arrives all by itself. A quarter turn. Do a quarter turn twice, and you have done a half turn. No cleverness is involved in that, and no trick. It is simply what quarter turns are. The thing mathematics had been unable to find for centuries, because it kept looking along the number line, was never on the number line at all. It was 90 degrees off it, at right angles, in a direction nobody had thought to look, because there had never been any reason to suppose the numbers had a second dimension. The square root of -1 is not a quantity. It is a rotation. And once you allow that, the whole landscape opens up in about 4 seconds. Start at 1, on the right. Turn a quarter circle counterclockwise, and you arrive at a point 1 unit above 0. That point is I. Turn again, and you are at -1. Again, and you are 1 unit below 0, at -I. Again, and you are back at 1. 4 quarter turns, 4 multiplications by I, and you have gone round the circle and come home, which matches the arithmetic exactly. I squared is -1, I cubed is I to the 4th is 1. Numbers were never a line. Numbers are a plane. Every complex number is a point on that plane, with a distance from the origin and an angle, and multiplying 2 of them multiplies the distances and adds the angles. That last sentence is the engine of everything that follows, so let it settle. Multiply the lengths, add the angles. That is what multiplication has always been. On the old number line, the angles were only ever 0 or a half turn, so nobody noticed there was an angle at all. The line was only ever a cross-section through something wider. Wessel saw it because he was a surveyor and thought in directions. Argan saw it because he was thinking about proportion and rotation as the same idea. Neither of them was a professor, and I suspect that is not a coincidence. The professors had spent their careers manipulating these things symbolically and had a great deal invested in the difficulty. The outsiders came at it with the eyes of people who had to make something work in the physical world. If you have been listening this far and want more of these, subscribe. There is a lot more to come tonight. Because a picture, however lovely, is not proof, and the mathematical establishment was not going to accept a diagram from a Danish surveyor or an anonymous Parisian. What the idea needed was the endorsement of somebody the profession could not ignore. It got the best endorsement available anywhere. Carl Friedrich Gauss was the son of a bricklayer in Brunswick, and by the age of 22, he was the finest mathematician on earth, a position he held without serious challenge for the next 50 years. The stories about his childhood are so numerous that some of them must be true. Correcting his father's payroll arithmetic before he could properly talk, being handed the task of summing the whole numbers from 1 to 100 by a teacher who wanted an hour's peace, and producing the answer within seconds by noticing that the numbers pair up. In 1799, at 22, he submitted a doctoral dissertation to the University of Helmstedt. Its subject was a claim that had been floating around for a century and a half without a satisfactory proof, and which we now call the fundamental theorem of algebra. The statement is this: every polynomial equation of degree 1 or higher, with complex coefficients, has at least one solution among the complex numbers. I want to unpack what that actually means, because the name makes it sound technical, and the content is anything but. Consider the history we have been following tonight. You start with the whole numbers, and you find you cannot always subtract, so you invent the negatives. Now you cannot always divide, so you invent the fractions. Now you find that the diagonal of a square is not any fraction at all, so you widen the system again to the irrationals, and you have the real number line. Every time, the same pattern. You ask an innocent question, the existing numbers cannot answer it, and you are forced to build a bigger house. The natural expectation is that this goes on forever. Add I, and surely something else will come along that the new system cannot handle, and you will have to add that too, and so on without end. That is not what happens, and that is the astonishing part. Once you have added this one number, the process stops, permanently. Any polynomial equation you can write down, of any degree, with any complex coefficients at all, including coefficients that themselves involve I, has all of its solutions already sitting inside the complex numbers. You never have to invent anything again. There is no equation lurking out there whose answer requires a fifth kind of number. Mathematicians call this being algebraically closed, and it is the deepest thing in this whole story after the casus irreducibilis itself. The complex numbers are the point at which the system stops leaking, rather than one more patch over the leak. Gauss's first proof had a gap in it, incidentally, a topological assumption he treated as obvious and which was only made rigorous in modern times. He gave 3 more proofs over the course of his life, the last in 1849, on the 50th anniversary of the first. Some men buy a watch. And in 1831, he did the other necessary thing, which was to make the plane respectable. He published a treatment of the geometric picture, arriving independently at what Wessel and Argand had already found, and gave the objects a proper name. Not imaginary, complex. Complex as in composite, made of 2 parts, the way you would say a complex of buildings. Not complicated, combined. He also wrote, in a passage that reads like an apology on behalf of his whole profession, that the difficulty people had with these quantities came largely from the bad terminology. If they had been called direct, inverse and lateral, instead of positive, negative and imaginary, he said, there would have been no obscurity at all. Lateral, sideways, at right angles, the number that lives just off the line. 2 centuries later, we still say imaginary. But once you had the plane, and once Gauss had blessed it, an obvious question presented itself to a certain kind of mind. If ordinary numbers live on a line, and complex numbers live on a plane, what lives in space? That question consumed one man for about 13 years, and he answered it while out for a walk with his wife. William Rowan Hamilton was an Irish prodigy, of the kind that seems slightly implausible when you read about it. He was reading Greek, Hebrew and Latin as a small child, had a working knowledge of a dozen more languages before he was a teenager, and was appointed Royal Astronomer of Ireland and Andrews Professor of Astronomy at Trinity College Dublin, while still an undergraduate. The post came with rooms at Dunsink Observatory, a few miles outside the city, where he was supposed to observe the heavens and was, by common agreement, not very good at it, because he was always thinking about algebra. He had reformulated the whole of classical mechanics in his 20s, in a way so elegant that when quantum mechanics arrived a century later, it turned out that Hamilton's formulation was the one that translated. Every physics student still learns the Hamiltonian. And for over a decade he tried to build a 3-dimensional number system. Complex numbers had done such wonderful work in the plane, describing rotations and oscillations with an economy nothing else could match. Space has 3 dimensions. Surely there should be a triple of numbers that worked the same way. His children used to ask him at breakfast whether he could multiply triples yet. He would say, sadly, that he could still only add and subtract them. He could not do it. Nobody could do it, and we now know why. There is no consistent way to multiply and divide in 3 dimensions. On the 16th of October, 1843, Hamilton was walking from Dunsink into Dublin with his wife, along the towpath of the Royal Canal, on his way to a meeting of the Royal Irish Academy. And as they walked, the thing he had been unable to do for 13 years arrived. The answer was to give up on 3 and go to 4. Not one impossible quantity, but 3 of them, which he called I, J, and K, each of which squares to -1, and which do not commute. I times J gives you K, but J times I gives you -K. The order in which you rotate matters, which anybody who has assembled furniture already knows in their hands. He wrote down the relation that ties it all together. I squared equals J squared equals K squared equals IJK equals -1. And standing on Brougham Bridge, where the canal passes under the road at Cabra, he took out a penknife and cut the formula into the stone of the bridge. He wrote about it afterwards to his son, saying that he could not resist the impulse, unphilosophical as it may have been. The carving is long gone, weathered off the parapet. There is a plaque on the bridge now, put up in 1958, and every October, mathematicians walk the towpath from Dunsink Observatory to the bridge in what they call the Hamilton Walk. He named a 4-part number a quaternion, and the part that was not the ordinary number, the 3-dimensional remainder he needed a word for. He borrowed one from Latin, from vehere, to carry. He called it a vector. Hamilton thought quaternions would be his monument, and spent his remaining 22 years on them, and for a while they were unfashionable, superseded by simpler vector notation. Then computers arrived. It turns out that if you want to represent a rotation in 3-dimensional space without the orientation of your object suddenly collapsing into ambiguity, quaternions are the clean way to do it. Every spacecraft that orients itself, every robot arm that swings a tool into position, every character animated in a video game or a rendered film is being turned by 4-part numbers invented on a canal towpath in 1843 by a man who was late for a meeting. 3 of the 4 parts square to -1. So far, this has been a story about mathematics arguing with itself. Now it becomes a story about the physical world, and the first place I comes ashore is somewhere you would never guess. It comes ashore in the wiring of your house. Charles Proteus Steinmetz was born in Breslau in 1865, in what was then Prussia, and is now the Polish city of Wrocław. He was born with a spinal deformity that his father and grandfather had also carried, and he grew to a little over 4 feet in height, with a hunched back and a hip condition that made walking painful. From childhood he was unmistakably marked out. He was also the outstanding mathematics student of his generation at the University of Breslau, and by his mid-20s he had completed everything required for a doctorate. The degree never came. He had joined a socialist student group and edited its newspaper. Bismarck's government was in the middle of a serious campaign against socialists, and when the police came for the editors, he left the country with the dissertation unsubmitted. Zurich came first, and then, in 1889, New York. Immigration officials at the port very nearly turned him away. He was visibly disabled, spoke almost no English, and had no money. A travelling companion vouched for him and talked the inspectors round, and Charles Steinmetz was admitted to the United States on somebody else's word. He found work with a small electrical firm in Yonkers run by another German immigrant, Rudolf Eichemeyer, and within a few years had done 2 things that mattered enormously. He worked out the law governing hysteresis losses in iron cores, which is the reason transformers waste energy as heat, and gave engineers a way to calculate it in advance instead of building a machine and hoping. Then he turned to a problem that was, at that moment, the central problem in the entire electrical industry. Something was happening in the electrical world of the 1890s that made this urgent. The current war was being fought and settled. Edison had built his empire on direct current, in which electricity flows steadily in one direction, and direct current is simple to understand and nearly impossible to send more than a mile or two without enormous losses. Westinghouse and Tesla were pushing alternating current, in which the flow reverses direction 60 times a second, and which can be stepped up to very high voltage for transmission and stepped back down for use. Alternating current wins on physics. It is why you have electricity in your house at all, rather than a generator on your street. But alternating current is much harder to calculate. With steady current, the arithmetic is easy. Voltage equals current times resistance, and you are done. With alternating current, everything is a wave. Voltage rises and falls 60 times a second. So does current. And in any real circuit containing coils or capacitors, the two waves do not rise and fall together. The current lags behind the voltage, or leads it, by some fraction of a cycle. Every component shifts the timing differently. To calculate a circuit, you had to track the phase relationship of every wave against every other, using calculus, with differential equations laboriously for every problem. Engineers in the 1890s were designing generating stations and transmission networks, essentially by trial, error, and educated guesswork, because the mathematics was too slow to keep up with the construction. In July of 1893, at the International Electrical Congress in Chicago, held alongside the World's Columbian Exposition, in a city glowing with the first great public display of electric light, Steinmetz stood up and delivered a paper titled Complex Quantities and Their Use in Electrical Engineering. It runs from page 33 to page 74 of the proceedings, so it was not a brief talk. His proposal was this: stop treating an alternating quantity as a wave that you track through time. Treat it instead as an arrow in the complex plane. Its length is the size of the voltage or the current. Its angle is the phase, the timing of the wave relative to some reference. That arrow is called a phasor, and once you have it, the letter I, which electrical engineers write as J because I already means current, becomes the operator that rotates a quantity by 90 degrees, and the calculus vanishes. That is the whole point. Differentiating a sinusoid in this representation becomes multiplication by J and a constant. Integrating becomes division. The differential equations that had been eating engineers alive collapse into ordinary algebra with complex numbers in it. Resistance, inductance, and capacitance stop being three different kinds of thing, requiring three different treatments, and become a single quantity called impedance, which is simply a complex number, its real part the resistance, and its imaginary part the reactance. Steinmetz's own description of what he had done was that it reduced alternating current phenomena to a simple problem in algebra. There was a competing proposal at the same Congress, incidentally. A Scottish-born physicist named Alexander Macfarlane had presented a paper a few pages earlier arguing for handling alternating currents with Hamilton's quaternions. The Congress heard both approaches, one using four-dimensional numbers and one using two, within the same session. The two-dimensional approach won completely, because it was the right size for the job, and Macfarlane's paper is now read by almost nobody. Steinmetz went to General Electric when it bought Eickermeyer's company and stayed for the rest of his life. He held over 200 patents. The arresters that protect transmission lines from lightning are his design, and he built an indoor lightning generator in his laboratory in Schenectady to test them, throwing artificial thunderbolts across a 100,000-volt gap in front of visiting reporters. He kept alligators, crows, and a Gila monster. A lifelong socialist, he corresponded with Lenin and Einstein, served as president of the Schenectady Board of Education, and made the city's schools among the best funded in the state. He never married, and he legally adopted his laboratory assistant so that he would have a family, and became a grandfather to that man's children. And every calculation performed by every power engineer since, in every utility on Earth, uses his method. The wiring in the walls around you was designed with I. That transformer, humming on the pole outside, was specified with it. Every grid carrying power across a whole country is planned, balanced, and protected with it. And so the quantity Cardano called useless became, within 350 years, the everyday working tool of the industry that lit the world. That would be a satisfying place to end. Something invented in confusion turns out to be enormously practical. But it is not the end, and it is not even the interesting part, because everything I have just described could in principle be done without complex numbers. It would be slower and uglier, and no engineer would thank you for it, but it could be done. The waves are real, so are the phases. The complex arrow is a bookkeeping device of extraordinary convenience, and if you took it away, you would still have your electricity. The question this whole story has been circling is a harder one. Is there anywhere in nature where I is not a convenience but a requirement? Anywhere it cannot be removed? For that we have to go to Vienna in the winter of 1925, and to a man who found the answer, hated it, and spent months trying to undo his own work. Erwin Schrödinger was 38 years old, which in theoretical physics is old, and had not yet done anything of the first rank. He had read Louis de Broglie's suggestion that matter, like light, might have a wave nature, and had been asked at a seminar in Zurich by Peter Debye why, if there was a wave, there was no wave equation for it. Over the Christmas holidays of 1925, he went to a villa in the Swiss Alps at Arosa, apparently with a woman who was not his wife, whose identity has never been established, and he came back with the equation. The Schrödinger equation is the central equation of quantum mechanics. It does for the atom what Newton's laws do for the solar system. Feed it a hydrogen atom, and out come the energy levels, exactly matching the spectral lines that astronomers had been measuring for decades, without knowing why they had the values they did. It is one of the great achievements of the human mind, and it appeared, essentially complete, in a series of 4 papers published through 1926, and it has an I in it, not tucked away in an intermediate step, sitting in the equation itself, multiplying the rate of change of the wave with time. The wave function is a complex valued thing. At every point in space, it has a magnitude and a phase, an arrow in the complex plane, and the whole apparatus depends on it. Schrödinger disliked this from the first day, and the record of how much he disliked it is among the more interesting things in the archives of 20th century physics. Look at what he actually does in the 4th of the 1926 papers, the one where the time-dependent equation first appears. He does not start with the complex equation. He starts by constructing a real one, a wave equation that is entirely real-valued, 4th order in space and 2nd order in time, and he says of it that this is evidently the uniform and general wave equation for the field scalar. There is even a remark that it resembles the equations that turn up in the theory of elasticity, the ones that describe a vibrating plate. That was the equation he wanted. Real numbers, no I, a genuine wave in the manner of sound or a drumhead. But a 4th order equation is a nightmare to solve, and it does not sit properly with the classical mechanics he was building on, so he factors the 4th order operator into a product of 2 2nd order operators, which are complex conjugates of each other, and he keeps one of them and throws the other away. That is where the famous equation comes from. 1st order in time, 2nd order in space, and complex, because it is 1/2 of a real factorization. The I in the Schrödinger equation is the residue of a factoring step, taken for mathematical convenience by a man who wanted the real version and could not make it work. He was completely open about not liking it. On the 6th of June 1926, he wrote to Hendrik Lorentz, the grand old man of Dutch physics, and one of the few people whose opinion he genuinely deferred to, and objected directly. "What is unpleasant here," he wrote, and indeed directly to be objected to, "is the use of complex numbers. Psi," he insisted, "is surely fundamentally a real function." Days later, he wrote to Max Planck, still working the problem, trying to reach a real formulation by differentiating twice with respect to time to get rid of the I. And at the end of the fourth paper itself, he tells the reader plainly that what he has given is a substitute, extraordinarily convenient for calculation, standing in for a real wave equation of probably the fourth order, which he had not managed to construct for the general case. The man who put the square root of -1 into physics spent the following months trying to get it back out again. He never did. Nobody has. And within months of that, somebody worked out what the complex wave function actually meant, and the answer came with a delay of its own that I find rather touching. Max Born was at Göttingen, running what was arguably the finest theoretical physics group in the world. He had been Einstein's friend for years, and would remain so through a long and famous correspondence in which the two of them argued about exactly this subject. In 1926, Born published a paper in the Zeitschrift für Physik, volume 37, pages 863 to 867, on the quantum mechanics of collision processes. He was studying what happens when a particle scatters off a target, and he needed to say what the wave function meant physically. Schrödinger had thought the wave was the electron, smeared out through space like a cloud. That interpretation runs into trouble almost immediately, because the wave spreads out, and electrons keep arriving at detectors as single, sharp, entire particles. Born proposed something different, and it was the sentence that split physics in two. The wave does not tell you where the particle is. It tells you the probability of finding it there. Now, in the main text of that paper, he wrote it slightly wrong. He said the probability was given by the amplitude of the wave. Then, reading the proofs before the paper went to press, he saw the error, and rather than reset the type, he added a footnote. The footnote says, in effect, that a more careful consideration shows that the probability is proportional to the square of the quantity. That footnote is the Born rule. It is the bridge between the mathematics of quantum theory and every measurement ever made. It is, arguably, the single most tested statement in the history of science, and it entered the world as a correction added at proof stage to a paper about particle collisions. Born waited a long time for that. Heisenberg received the Nobel Prize in 1932, Schrödinger and Dirac in 1933. Born, whose interpretation made the whole structure mean anything at all, waited until 1954, at the age of 71. He had by then spent the war years teaching in Edinburgh, having left Germany in 1933. Two of his former students, Fermi and Oppenheimer, had gone on to build reactors and bombs. His granddaughter, incidentally, is the actress Olivia Newton-John. Why the square, though? Why not the amplitude itself? Because of what kind of thing the wave function is. And this is where every thread of tonight finally ties together. The value of the wave function at a point is a complex number. That means it has two pieces of information in it. It has a length, its distance from the origin in the complex plane, which we call the modulus, and it has an angle, its direction, which we call the phase. Squaring the modulus throws the phase away completely. A quantity at angle 30 degrees and a quantity at angle 290 degrees, if they have the same length, give exactly the same probability. The phase makes no difference whatsoever to what you measure, which sounds like it makes phase irrelevant, a piece of scaffolding you could take down after the building is finished. It is the opposite, and the reason is interference. Suppose a particle can get from where it starts to where it ends up by two different routes. An electron leaving a filament and arriving at a screen, with two slits in a barrier in between. It could go through the left slit or the right one. Quantum mechanics says you do not choose. You take the complex number associated with the left route and the complex number associated with the right route, and you add them together as arrows in the plane. Then you square the length of the result, and that gives you the probability of the electron landing at that spot. Watch what happens when you add two arrows. If they happen to point in the same direction, they add nose to tail, and you get a long arrow. Square it, and the probability is high. The electron lands there often. If they point in opposite directions and have the same length, they cancel completely. The result has zero length, and squaring zero gives zero. The electron never lands there. Two routes, each of which on its own would deliver the electron to that spot, together deliver it nowhere. And everything in between, depending on the angle. The angle between those two arrows is the phase difference. The individual phases are invisible, permanently, in principle. You cannot measure the phase of a wave function any more than you can measure the absolute height of the sea without agreeing on a datum. But the difference between two phases is perfectly visible. It is written directly onto the screen as the pattern of bright and dark bands that has been photographed in every physics department on Earth, which gives you the sentence that this whole story has been traveling towards for 11 sections. The part of the number you can measure is the modulus. The part of the number you can never see is the phase. And the part you can never see is the part that decides where the electron lands. That is a genuinely strange thing to be true about a universe. There is a quantity woven into the mathematics of matter which is unobservable in itself, and which nonetheless determines the observable outcome, because outcomes depend on differences of it. Now, a reasonable person, hearing that for the first time, will raise a reasonable objection, and it is the same objection Schrödinger was raising in his letter to Lorentz. If the phase is unobservable, perhaps it is not real. Perhaps it is an artifact of a convenient notation, like the imaginary part of the impedance in an alternating current circuit, and a cleverer formulation would express the same physics without it. That objection stood, unresolved, for a very long time, and the first serious crack in it came from an effect so counterintuitive that when it was first predicted, the prediction was ignored, and when it was predicted again 10 years later by different people, it caused an argument that lasted 25 years. Consider a solenoid, a tightly wound coil of wire carrying a current, which you can picture as a small cylinder a few centimeters long. Inside such a coil there is a strong magnetic field. Outside an ideal one, there is no magnetic field at all. The field is confined, entirely, to the inside of the cylinder. Now put that solenoid behind the barrier in a double-slit experiment, in the shadow between the two slits, and shield it so that no electron ever touches it or enters the region where the field is. The electrons pass on either side. They travel through a region where the magnetic field is precisely zero, everywhere along both paths. They feel no force. Nothing in classical physics can act on them, because in classical physics the field is the thing that acts, and there is no field where they are. The interference pattern shifts. Turn the current in the solenoid up, and the bands slide sideways across the screen. Turn it off, and they slide back. The electrons are responding to a magnetic flux that exists only in a region they never visit. That is the Aharonov-Bohm effect, and it is one of the strangest facts in physics. The history of it is a small tragedy of the kind this story keeps producing. It was first worked out in 1949 by Werner Ehrenberg and Raymond Sidé, two physicists in Britain, who published it in a paper about the refractive index of electron optics. The result is in there, correct and complete. Nobody noticed. The title gave no hint of what it contained. The journal was not one that theorists watched closely, and the paper vanished into the literature for a decade. In 1959, Yakir Aharonov and David Bohm, working at Bristol, derived it independently and published it in the Physical Review, volume 115, page 485, with a title that said plainly what was at stake: significance of electromagnetic potentials in the quantum theory. This time the physics community heard it and immediately began arguing, because the result appeared to say that the potentials, which had always been treated as a mathematical convenience with no physical reality, were more fundamental than the fields. Bohm, incidentally, was in Bristol because he had been driven out of the United States. He had been Oppenheimer's student at Berkeley, was called before the House Un-American Activities Committee, refused to testify against colleagues, was indicted for contempt, acquitted, and then quietly not renewed by Princeton. He went to Brazil, then Israel, then England, and did some of his best work in exile. The first experimental confirmation came the following year, in 1960, from R.G. Chambers at Bristol, published in Physical Review Letters, volume 5, page 3. He used a tapered iron whisker, a microscopic magnetized needle, as his confined flux, and saw the fringes shift. Skeptics were not satisfied, and their objection was fair. No real solenoid confines its field perfectly. Perhaps a trace of field was leaking out along the electron paths and doing the work in an ordinary way. Settling that took 25 more years, and a piece of experimental artistry that I think is underappreciated. Akira Tonomura and his colleagues at Hitachi's laboratory in Tokyo, through the 1980s, built the definitive version. They fabricated tiny magnets in the shape of a donut, so the flux ran round the ring with no ends to leak from, and coated them in a superconducting layer, because a superconductor expels magnetic field entirely and would push any leakage out. Then the whole assembly was cooled, and electrons were fired through the hole in the donut and around the outside, and the two compared. The fringes shifted, exactly as predicted, in a region where the field was zero to the limits of anything measurable, with the leakage physically excluded by superconductivity. The electron acquires a phase from a magnetic flux it never encounters. That phase is out there in the world, doing something, rather than sitting quietly in a ledger. And in a result from Stanford published in Science in 2022, a version of the same effect was seen with gravity. Chris Overstreet, Peter Asenbaum, Joseph Curti, Minjong Kim, and Mark Kasevich launched clouds of ultra-cold rubidium atoms up a vacuum tower 10 meters tall, split each atom into a superposition following two paths separated by about 25 centimeters, and placed a tungsten mass of 1¼ kilograms near the top, so that one path passed closer to it than the other. They ran the experiment with the mass and without it, with paths near the mass and paths further away, and pulled out a phase shift that could not be accounted for by the gravitational force deflecting the atoms. An atom in two places at once, 25 centimeters apart, keeping track of the difference in the gravitational potential between them and reporting it in its phase. So the phase is physical, that much is settled, and has been for a long time. But settled is not the same as necessary, and here the argument takes its final turn, because a determined objector can still say the following, and for most of the 20th century, nobody could answer it. Yes, the phase is real. Yes, interference is real. But a phase is just an angle, and an angle can be written down with real numbers. Give me two real numbers instead of one complex number, and rules for combining them that mimic complex multiplication, and I can reproduce everything you have just described without ever writing the letter I. The objection is far from foolish. It is very nearly right, and for a long time it looked as though it might be entirely right. In 1960, Ernst Stueckelberg, a Swiss physicist of enormous originality, who spent his career being slightly ahead of everyone and slightly ignored, showed that quantum mechanics could indeed be formulated in a real Hilbert space, with an extra operator doing the job that I normally does. It worked, and the predictions came out the same. Later work sharpened the point further. For any single experiment you care to name, however elaborate, a real number version of quantum theory can be constructed that reproduces the results exactly. If the question is whether complex numbers are necessary for any given laboratory measurement, the answer, for decades, was plainly no, which left the whole thing looking like a matter of taste. The complex formulation is elegant and compact, the real one is clumsy but adequate, and choosing between them is aesthetics rather than physics. Most working physicists, if you had asked them in the year 2000, would have said something along those lines and gone back to work. Then, 8 people found a way to turn the question into an experiment. The paper is titled, "Quantum Theory Based on Real Numbers Can Be Experimentally Falsified." It appeared in Nature, volume 600, pages 625 to 629, on the 15th of December, 2021. The authors are Marc-Olivier Renou, David Trillo, Miriam Weilenmann, Tin Lei, Armin Tavakoli, Nicolas Gizin, Antonio Assin, and Miguel Navasquez, working between Barcelona, Vienna, and Geneva. Their insight was about networks. All the earlier results about real number quantum theory concerned a single system, prepared once and measured. In that setting, the extra structure a real formulation needs can always be hidden away somewhere, and the mimicry succeeds. But modern quantum experiments run on networks. You have 2 separate sources of entangled particles, built independently, sitting in different places, sharing nothing. Source 1 sends a particle to Alice and another to Bob. Source 2 sends a particle to Bob and another to Charlie. Bob, in the middle, holding one particle from each source, performs a joint measurement on both of them at once, which has the effect of entangling Alice's particle with Charlie's, even though those 2 particles have never met and came from unrelated origins. It is called entanglement swapping, and it is the basic operation of a quantum network. The independence of the 2 sources is the crucial ingredient. In the standard complex formulation, you can insist on it cleanly. In a real number version, reproducing the same correlations requires the 2 independent sources to share something after all, some hidden coordination that the complex version does not need. So the 2 theories, which agree everywhere else, come apart. Renou and his colleagues designed a game to be played across such a network, with a score you can compute. Standard quantum mechanics predicts one maximum score. A real number quantum theory, obeying the same independence assumptions, cannot exceed a lower one. 7.66. It is precisely what John Bell did in 1964. Bell took a question that had been argued philosophically for 30 years, whether the world might be running on hidden variables underneath, and converted it into a number you could go and measure. Renou and colleagues did the same for the complex numbers. A 300-year-old question about the nature of a mathematical object became a laboratory procedure with a threshold. Both experiments were published on the same day, the 24th of January, 2022, in the same issue of Physical Review Letters, back to back. Ming-Cheng Chen and colleagues at the University of Science and Technology of China, in Hefei, built the superconducting version. Their paper is at page 040403, and the system is a superconducting processor, circuits patterned in metal on a chip, cooled in a dilution refrigerator to a few thousandths of a degree above absolute zero, colder than deep space. They ran the entanglement swapping game with an entangling fidelity of about 0.95 and measured a score that exceeded the real number bound of 7.66 by 43 standard deviations. 43 standard deviations is not a marginal result. Particle physicists declare a discovery at 5. 43 is a number you quote when you want to say that the possibility of a statistical accident has been removed as thoroughly as any human being knows how to remove it. Jung Da Lee and colleagues did the optical version, printed as the companion paper immediately before it in the same issue, using photons, beam splitters, and detectors rather than superconducting circuits, and reached the same conclusion by an entirely different physical route. 476 years after Cardano wrote that arithmetic subtlety had reached its useless extreme, two laboratories on opposite sides of the same question put a number on it. Now I want to give you the honest version of what that means, plainly, rather than burying it at the end where it will not disturb the story. This part matters, and the popular coverage of it in 2022 was, in places, considerably more confident than the physics warrants. What the result establishes is that within the standard formalism of quantum theory, under the stated assumptions, the real number version cannot reproduce what nature does. Those assumptions are specific. They concern how independent systems are combined, what a measurement on a composite system is allowed to be, and how the sources are required to be uncorrelated. What the result does not establish is that no reformulation of physics could ever avoid complex numbers. If you are prepared to add extra structure, to change the rule by which independent systems combine, to carry additional degrees of freedom, you can construct real valued descriptions that are not touched by this theorem. Several physicists have published exactly that argument in the years since, and the exchange is still going on in the journals. Some of the pushback is about the framework, some is about how the headline was phrased, and the discussion is a healthy one rather than a scandal. So the honest statement is this: within the framework, physics actually uses, day to day, the complex numbers are not removable, not slow to remove, not inconvenient to remove, not removable, under the assumptions that framework makes. And that is a far stronger claim than anyone could have made in 1926, when Schrödinger was writing to Lorentz, insisting that psi was surely fundamentally a real function. He thought it was a matter of finding the right formulation. It turns out to be a matter of what the world will and will not permit. Cardano's mental torture is now a laboratory result. Let me draw the whole thread together, because I think the shape of it is the most beautiful part, and it is the thing worth carrying with you into sleep. Richard Feynman gave a lecture at Caltech in the early 1960s, in the first volume of what became the Feynman Lectures on Physics, and it is unlike anything else in that course. He does no physics at all. He begins with the whole numbers, and rebuilds arithmetic from scratch, generalizing one step at a time. Addition, then multiplication as repeated addition, then powers. Then he starts asking about inverses. Subtraction demands negatives, division demands fractions, roots demand the irrationals, and logarithms of negative numbers demand something else again. And each time, he says, we invent the thing we need, and each time we check whether the rules still hold, and each time they do. He arrives, near the end, at the relation Euler found around 1740. The exponential of I times an angle equals the cosine of that angle plus I times the sine of it. And you can almost see why it has to be true, from the picture the surveyor and the bookkeeper gave us. Exponential growth is what you get when the rate at which a thing changes is proportional to the thing itself. Money in an account, bacteria in a dish. Anything that grows faster, the more of it there is. The growth always points in the same direction as the quantity, straight outward from where you are. Now make that constant of proportionality I, instead of an ordinary number. Multiplying by I turns a quantity through a right angle. So the rate of change is no longer pointing outward along the quantity, it is pointing at 90 degrees to it. And a point whose motion is always exactly perpendicular to its own position can never get any further from the origin, and can never get any closer. It can only go round. That is what a circle is. and travelling round a circle at a steady rate is precisely what the cosine and the sine describe. So an exponential with an I in it does not grow. It turns. The formula saying so is the same fact the Danish surveyor noticed in a cold field, written out in the language of calculus. That single line says that exponential growth and circular motion are the same phenomenon viewed from different directions, and that the connection between them runs through I. It is the reason complex numbers describe every oscillation, every wave, every rotation, every alternating current, every quantum amplitude. And if you set the angle to half a turn, it collapses into the identity that links E, I, pi, 1, and 0 in 5 symbols, which is the piece of mathematics most often described as beautiful by people who have no other interest in the subject at all. Feynman called it the most remarkable formula in mathematics, said it was the jewel, and then spent a lecture setting it properly, the way a jeweler sets a stone. That is where the road ends. And look at where it started. It started with a lecturer in Bologna who solved a problem and told nobody. From there, it ran through a boy with a sabre wound in his palate, who taught himself to read from a stolen copybook, and then beat the man holding the greatest secret in Italian mathematics. Then a physician who broke an oath, credited his sources anyway, performed the first complex calculation in history, called it useless, and went to bed. Then a drainage engineer in a borrowed villa who had a wild thought and made the impossible thing behave. Somewhere in there, it picked up a dismissive name from a philosopher who was thinking about something else, and has been carrying that name ever since like a scar it never asked for. Then a Danish surveyor who spent 40 years measuring cold fields, and a Parisian bookkeeper too shy to put his name on his own pamphlet, independently noticed that the thing everyone had been searching for along a line was sitting at right angles to it, and that what they were looking at was a quarter turn. Once you see that, the imaginary axis stops being mysterious and becomes simply the direction nobody thought to look. Gauss made it respectable and proved that arithmetic, having swallowed this one number, would never need another. Hamilton, walking the towpath of the Royal Canal, found the 4-dimensional version and cut it into a bridge with a penknife, and it is orienting satellites tonight. Steinmetz turned it into the working arithmetic of the electrical grid, and it is in the wiring around you. Schrödinger put it into the heart of matter and spent months trying to take it back out. Born squared it in a footnote and told us what it means. And a network of laboratories, 476 years downstream, checked whether it could be avoided, and found that it cannot. Cardano was right about one thing. It is a strange business, reaching a real answer by way of a place that is not there. He simply misjudged which side of the strangeness the truth was on. The detour turned out to be the road. It always had been. There is one more thought I would like to leave with you, and it is not really about mathematics. Every enlargement of what counts as a number has arrived the same way. Somebody is doing an ordinary calculation, following rules that have always worked, and the calculation hands back an object the existing vocabulary says cannot be there. The first response, every time, is to declare the object false. 0 is not a number, because it is the absence of number. Negatives are not numbers, because you cannot have less than nothing. The diagonal of a square is not a number, because it is no ratio of whole numbers. Each of those was a settled position held by intelligent people, and each of them dissolved, not because anybody won an argument, but because the objects turned out to be consistent and useful, and finally too convenient to keep refusing. What 4 centuries suggest is that the mathematics tends to run ahead of the intuition, and that when a calculation insists on something your vocabulary cannot hold, the sensible move is to widen the vocabulary rather than accuse the calculation. Bombelli did that in a borrowed villa in the Val di Chiana. Cardano, who was cleverer and better educated and had the whole thing in his hands first, did not, and it cost him a place in a story he had opened himself. None of which means that everything strange turns out to be true. A great many strange things are simply wrong, and being told you cannot have something is usually good advice. The lesson is narrower than that, and it is that consistency makes a better guide than familiarity, which is worth holding on to the next time something arrives that does not fit. So the next time somebody tells you that imaginary numbers are not real, you will know what to say, and you will be able to say it kindly, because the name has misled better people than either of us. They are not imaginary. They never were. What they are is the direction the number line forgot to mention, and the universe, as far as anyone has been able to test, does its arithmetic in the plane. Sleep well. There will be another one of these next week, another old idea taken slowly apart in the quiet. Subscribe, and it will be waiting for you.